one of the things that is exciting the community, especially people outside of robotics that are entering the community, is the fact that there is a low barrier of entry access at the beginning, especially, I'm thinking, for example, of, soft pneumatic actuators at sort of like a centimeter scale. They've been around for almost, I guess, more than a decade actually. And people can build them really easily. I have had students that, built them at home out of a 3D printed mold that they were able to manufacture, or even just like out of scrap materials that they had available in their homes, and they were super excited. And so that's great, I think, about our community. But from a fabrication point of view, I think there are still many challenges that we are facing when we scale down these mechanisms, and exactly, again, for minimally invasive surgical applications, for example. So I think integrating, again, those sensors, those actuators, and maybe that distributed level of control that we would want in those soft micro robots is going to take obviously some more research, and that's where the challenges are going to be, but also the excitement, I think.
In this podcast, I'm sharing my passion and curiosity for soft robotics, where we share inspiring stories about the work we do and how we can push the limit. I am Mara Dwini, and this is Soft Robotics Podcast. Support for this show comes from Science Robotics Journal. I really find Science Robotics to be a great resource for reliable and tangible research where we can really push the limit of the science we do in robotics. Great way to stay up to date with the published article is checking out the released monthly issue. All the links will be included in each episode description. We will also happen to have a regular conversation on the most published science robotic articles, where also you can contribute with your question and thoughts about the research. Thanks Science Robotics for sponsoring Soft Robotics Podcast. So maybe I'm curious to ask you, I think your mission about how you can design soft robotics for surgical application. I'm curious to ask you if you have like a grand picture, what is maybe challenging for designing soft robotics in the sense of surgical application?
Yeah, definitely. Well, the challenges of designing a soft robot for surgical applications, I would say, especially if you're new to the field, the very first things that you will encounter, for example, like say you're a new PhD student in the lab, is the fact that if your background is in engineering and robotics, you'll have to sort of like train yourself to communicate with surgeons, right? Typically, surgeons and engineers tend to speak two different languages. And so I think the very first challenges are to understand what the clinical requirements are and making sure that the robot that you're building is going to be meeting them. I think as engineers, we are really good at understanding, the problem that we are facing and engineering, obviously, a solution to it. But typically, clinical surgical applications have very strict type of specifications when it comes to, for example, having a robot that can interact with with biological tissues, or inside the body you have delicate organs, like think, for example, about the brain, or think about, for example, lungs, which are certain districts or areas that we are, for example, working on. You have to be very careful how you build your robot, what materials you're going to be using. They should be, biocompatible. You should make sure that even if parts of the robot is going to fail, like say, for example, an actuator is going to fail, is not going to harm the human body. And so, for example, using soft fluidic actuation makes a lot of sense, because especially if you're inside the body and you have a leak of saline solution or water, it's still going to be safe. But all of these aspects are really, the very first things that I think you have to think about when you are approaching soft surgical robotics.
Great. Since you're already focusing maybe in the mechanical part on the design, and I don't know, how do you see if you, after consideration from the surgical part, but this kind of biocompatibility with the forces required, all this kind of the features you want in the design. How do you approach the design process at the first step here?
Yeah, so I would say, a soft robot is made out of different components. There is the actuation, the sensing. We are definitely mostly focusing in the lab on the hardware side, so more mechanical mechanisms and these types of hardware components. And so the way that you approach the design of all of these parts is by selecting at the very first step, the materials that you're going to be using, obviously. And obviously, the very first prototypes that you're going to be building don't necessarily have to satisfy all requirements. Like, for example, biocompatibility is not probably the very first thing that you're going to be thinking of for the very first proof of concepts that you're going to be building. But you have to have in the back of your mind some level of knowledge that that's what you're shooting for. And so there is the selection of the materials, there is the selection of different structures that you're going to be designing. And then there is also, a constant back and forth discussions with our clinical collaborators. In the lab, we have, I would say, several surgeons that are working with us. They're really interested and excited about the technology that we're developing. And my students typically get to experience, they shadow these surgeons in the operative room. They try and understand what are the current challenges that they face on a daily basis before they can engineer a solution, that they can design a solution. And then there's a lot of iterative process, going back and forth, what works, what not, to build and engineer a solution.
Mm-hmm. And if you can dive deep in the material part, because I think you're also focusing how can we use the soft materials with hard parts. If you get us, because I think it's very interesting what kind of functionality you're looking for when you integrate different classes of material in one structure. What is the purpose? What a function you look for when you try to combine different classes of material?
Yeah, that's a really good question. Well, to me, soft robotics is, I would say the definition of soft robotics is expanding, right? Because a soft robot it's literally what the word says. It's a robot made out of soft materials. But in my lab, we are also using other types of materials, like you're saying. And the reason why we're doing this is sort of like combining, creating soft hybrids. So robots made out of soft materials and rigid materials, because we are looking at sort of like combining the best of both worlds, especially for the types of applications that we have in mind. So if you go again in surgical clinical applications, there are especially minimal invasive surgery, so using robots to access hard to reach locations in the human body by accessing through a very small opening, for example, without performing large cuts in the patient's body. You have to build something that is really miniaturized to do that. So a very small robot that can access, for example, the mouth and navigate inside our lungs or in our stomach. And so it has to have a very small footprint. And so when you scale down soft robots, they don't necessarily perform as well with the type of applications that we have in mind. So, for example, that means that they will not be able to exert very large forces and, for example, grasp tissue, biological tissue, to then, for example, perform a cutting or surgical procedure. And so what you have to do is sort of like take a step back and say, oh, well, if I scale down these soft robots and they are not going to be able maybe to reach the performance in terms of force output or power density that I need, then maybe I have to think about engineering a different solution. And combining soft materials with hard materials is, very easy, obviously. In my lab, we are looking at especially combining soft actuation, soft sensing together with rigid origami inspired mechanisms. And so this is mostly to create, the result of this is creating, soft foldable robots. So robots that can be folded in really tiny compact configurations. And so, for example, be mounted around an endoscope or a catheter, in traditional medical instrumentation, for example, and can be very small in that configuration, and, for example, navigate to the surgical target area that you want to reach, like, say, for example, the lungs. And then once you reach that target area, they can be unfolded and deployed by using these rigid origami components, and having flexible joints and stretchable joints, for example. Using that soft part is really useful. Especially soft materials are useful when you want to ensure that the interaction between the robot and the environment, for example, the body is safe, and so you're not going to scratch, you're not going to harm the surrounding biological tissues.
Mm-hmm. Do you have any moments was maybe challenging a design, given what situation you mentioned? It was kind of a challenge how you design something safe and exert enough forces, and be also navigate through this kind of tiny places like mouth, whatever, stomach. Do you have any moments like it was challenging a design?
I wouldn't say that we had challenges. I think all of this is part of, obviously, years of training and experience. And so, like in everything, I guess, in life, at the beginning it's more difficult, and then it gets easier as you gather experience, as you gather knowledge, and you become more familiar with the field. So probably, yeah, maybe, if you asked me this question maybe 10 years ago, the answer would have been, different. But I think it's mostly the experience that you develop, and obviously working in a large community, there is a lot of potential inputs and inspiration that you can get. So I wouldn't say like there is really a challenge behind that. To answer your question, maybe I have to think about, younger students in my lab, and the challenges that they are facing when they are approaching this research for the very first time. But I think part of the training that I ask them to go through is really get exposed to all of these different experiences in terms of shadowing surgeons in the operative room, and talking to people in the robotics community, in the soft robotics community, and outside the community, and obviously, reading papers, gathering that knowledge as much as possible. But I have to say, really, I don't see these as challenges, because, and maybe I am biased, but I think the field that we are working on is very exciting, and I tend to get that level of excitement and enthusiasm from students that are joining my lab, and the community in general as well. And I think they are not really worried about this as a challenge. Like, how do I learn how to design a robot, fabricate a robot for surgical applications? It doesn't sound daunting for them. I think they're really excited about the fact that, the research that they are doing today is going to have an impact in the future. It's something that I have always found really motivating for me as well. Like waking up in the morning, stepping into the lab, working on these really cool soft surgical robots, and having in mind that you are, for example, targeting some of the projects that we have, for example, currently in the lab, have to deal with developing soft surgical robots for interventional bronchoscopy. And, for example, lung surgery is really important, because lung cancer is one of the deadliest cancers these days. And the fact that you are working on a project that can potentially one day have a positive impact on such a an important disease is really motivating. And so I don't think, that you really focus too much on these challenges as much as you focus on the fact that what you are doing can have such a great impact in the future, like say 10 years from today.
Yeah. Maybe a question about the interesting parts, or maybe the still need more research, or still maybe not solved it fully. You also focus on topology and geometry. I don't know how you see the design of the shape of the robot or the complex topology. If you are not just having at the beginning, you sense that biocompatibility maybe is not the first priority, but if you speak about the shape of the robot or the topology, you are interested in that? Do you think there's something here?
Yeah, of course. So part of the design process that we are working on as, for developing these soft foldable robots that I mentioned, part of the design process is really imagining, a resulting 3D structure that you're going to be building out of 2D layers. Let me clarify this. So in the lab, we are working on manufacturing technologies that, as I mentioned, combine soft materials and hard materials. And the way that we are combining the two is by basically creating soft layers, soft films, if you will, out of soft biocompatible elastomers, out of soft lithography. And so these are literally just 2D layers of, for example, actuators or sensors that we fabricate, and then we laser cut, and we assemble with other rigid layers, rigid films of materials that have been laser cut, and then we use chemical surface modifications to bond all of them together so that we make sure that the interface between these soft components and hard components is sort of like seamless, if you will. By designing each layer separately in 2D and then assembling them and stacking them literally as sort of like a sandwich, then you go back with other types of machining, such as, for example, again, laser machining, to sort of detach your robot from that scaffold, and at that point you're able to pop up the robot and make it move and fall into the desired 3D shape. And so yes, topology, geometry, they play an important role into the design. The challenging part is probably at the beginning, going back to your previous question, trying to train yourself on how you're going to be imagining the final topology, the final geometry that you want to achieve in 3 dimensions by designing these 2D layers of different components. And so it's sort of like a different type of reasoning, if you will. So when you were, for example, building a hard robot directly in 3 dimensions using, your CAD modeling software, you were able to assemble actuators and components directly, like, say, for example, you had a specific DC motor in mind that you were going to be building, you would put it in there and you would know immediately in 3D how the structure is going to look like. In our case, we're mostly designing these components in terms of like layers, and so you will know what type of layer of sensors is going to be embedded in a specific configuration, in a specific location of the body of your robot, and then you have to imagine how that is going to shape in 3D, how we are going to be distributing these soft sensors and actuators, for example, inside the body of the robot. The advantage of having this type of approach is mostly, I would say, the possibility of embedding distributed actuation and sensing more easily. The fact that you can play with a variety of different materials, whether they're hard, whether they are soft, biocompatible components, structural components, flexible, stretchable components, and you can basically embed whatever type of material you want into the robot based on the structural and the structural functionality and overall the shape that you want to achieve.
Great. And for the sensing part, do you also think, I don't know if you agree that we have to reduce the sensing capabilities in the robot and just depend on physical intelligence. How do you see the approach of embedding sensing in surgical robotic when it comes to robotics? What's the strategy for that? Yeah.
That's actually a really important point. So I would say for a number of years, at this point, for more than 2 decades, we've had surgical robots available in the operative rooms, and we've seen a lot of robots really being created for surgical applications. Some of them are commercial platforms, some of them are more sort of like research platforms. So, the community is not new to this specific applications of robotics, but sensing in itself for surgical robotics is something that for some reason has been more challenging to integrate. And I believe that reason is mostly the fact that surgical robots are very small, as I mentioned. And so integrating in something that is so small, that has to be miniaturized, all those different components that you need, including, for example, sensing, is challenging, right? And if you think about, traditional methodologies of sensing, that would probably require, a lot of wires and cables coming out of your robot. And typically, when you are dealing with, I don't know, sort of like more industrial types of applications, you're not really worried about, cables coming out and potential shorts, electrical shorts. But when you are inside the body, obviously you have to take care of that somehow. And so sensing to me has been more of a challenge. And because of the fact that this has been so difficult to implement, some of the surgical robots that are out there, they don't necessarily provide haptic feedback to the surgeon. And so surgeons still have to rely on visual cues when they are performing, for example, robotic surgery. Visual cues means, for example, that as you are manipulating a biological tissue, you have to approximate the amount of stretching that you are applying onto the tissue to the force that you are applying onto that specific piece of tissue. And that is not necessarily good, because you could, for example, apply too much force and potentially tear tissue, cause bleeding, hemorrhage, for example. So sensing is becoming more and more of an important aspect, and integrating sensors inside these surgical robots, obviously is going to make them smarter and more reliable. And the outcome obviously is going to have better surgical outcomes, better patient outcomes, and safety as well. So in my lab, we're working a lot on sensing aspects, including, for example, soft optical sensing. We recently published a paper on a soft robotic sleeve that can be mounted around, for example, endoscopes, specifically colonoscopes, for improving interventional colonoscopy, so interventional robotic colonoscopy. One of the problems, for example, that colonoscopies have is that as you are navigating inside the colon with an endoscope, typically clinicians they have to push the colonoscope, obviously, to reach inside the body, inside the colon. And by pushing, they can exert too much force. And potentially that force can cause bleeding and perforations in the colon. But they don't really know, because they only have visual feedback from the camera that is positioned at the tip of the tool. They don't really have information about the force that the overall endoscope is applying onto the colon. And so having, sensor feedback, haptic feedback becomes paramount to ensure that these procedures are going to be safe and less invasive in the future, such that the vast majority of people would want to have a colonoscopy, for example, or they would want to have a safe access to these surgical procedures.
Mm-hmm. Right. But I'm going to ask you again about, because you mentioned that will be impactful maybe in 5 or 10 years, but the scenario failure, for example, for the sensor itself, if the sensor failed to sense something, also mechanism of actuation fail, how do you see the redundancy here? Because if the sensor failed, how would we do know what the alternative? How do you think about redundancy in such critical application like that?
Absolutely, very important. one sensor, yes, obviously could fail and could not necessarily return the information, the important information that you're looking for. So redundancy of sensor is very important. And the thing that I mentioned before, distributed sensing and actuation in our soft surgical robots, is something that we are looking for on a daily basis in the lab, just to ensure the fact that one sensor or one actuator, if they fail, you're going to have some level of safety, to continue that specific surgical procedure that you're performing with the robot. That is, I would say, not new, is something that has been used in the surgical robotics community for a long period of time. So having that level of redundancy of sensors, having that level of redundancy in actuators, as well as having a lot of, I would say, lines of codes implemented in the robot. So like, for example, if you're thinking about the Da Vinci robot from Intuitive Surgical, it had a massive amount of lines of codes for safety, for extra safety. With soft surgical robots, the interesting thing is that, the community is really making the case that maybe because our robot is soft, maybe because it's safer with respect to more sort of like traditional rigid robots, we will reach a point in time where we don't really need to worry too much about, the control side of things. It's still going to be obviously there, but we are going to be able to exploit the softness of the materials that we are using to have that extra level of safety.
Mm-hmm. And I'm curious to ask you, do you have any questions you still ask yourself, or maybe in the community in soft robotics, maybe still not really answered, or maybe ask about the community? Do you have any question you would like to share? Maybe in your group also.
Yeah, I think there are still, obviously soft robotics, soft surgical robotics are really growing, exciting fields, vibrant fields to be in. And so I believe there are still a lot of open questions that we still have no answer for, right? And so I think maybe if I can think of one off the top of my head right now is the fact that, we're building these soft robots out of soft materials and soft actuation sensing components, but there are still a lot of these components that are part of the puzzle of building a soft robot that are under research and development, and they are not quite ready maybe yet. So, the powering aspects, the battery aspects, how are you going to be safely powering a soft robot, for example, for surgical applications? It's still something that is a lot under development. Now, for a long period of time, we haven't necessarily worried too much about this, because many of the surgical robots that are out there are tethered by definition, and so you can use that tether to provide, for example, power to the robot. But that's probably not necessarily going to be true for the next maybe 10 or 15 years, and so those challenges are something that the community is going to be probably looking at sometime soon.
Mm-hmm. And I'm curious also about your thoughts in the material part. Do you think you would be in favor using material that work as both actuator and sensor, that we can avoid embedding sensing and maybe cause us trade-off in the design? I don't know how you encounter this kind of decision to select the material and how to embed the sensor. Do you think you're in favor for using material can be work like any conductive polymer, just for example? For you, what do you think about that?
That makes absolute sense, yes. So using, what you would call a smart material, right? What you would call a material that can be responsive to a stimulus and, for example, provide actuation or provide information, sensing. That makes perfect sense. In the lab, we haven't explored specifically ionic polymers or other types of materials like these, just because in the back of our mind, we always have that level of question of, is this safe? Is this going to be safe to use inside the body? What are the currents that we need to apply? What's the temperature that the material is going to develop and inside the body, and so on. So I think, it is important as soft roboticists to collaborate with people from, for example, the material science community, people that are developing these new materials, and communicate with them what are the specifications, maybe that we would look for if we had the possibility of creating an ideal material. And obviously, maybe the specifications that I would have are different from another soft roboticist working in the community if they are looking for a different type of application, obviously. But I think at the end of the day, what makes the soft robotics community really exciting is the fact that, we have all of these diverse group of people that are working in it. So, traditional roboticists, material scientists, and so on, that can collaborate together to create something, that we cannot maybe imagine today, but will be possible in the future. And creating that level of discussion and diversity in the field, I think is really one of the keys of the success of the field.
Mm-hmm, mm-hmm. I don't know if you have any highlights in this journey about something was maybe surprising or exciting. Like, for example, if you do something and it was counterintuitive in their behavior, or you didn't expect it to start to behave like that. Do you have this moment of excitement, or this was surprising? Do you have this moment?
Oh, wow. Well, yeah, I cannot think of a specific one. I think more that this is a type of feeling that happens on a daily basis, I would say. It's more like, as someone who's, again, really more sort of like a hardware person and working on hands-on things in the lab. I think when you build something and you test it and you examine the behavior of the robot, you analyze the data that you are gathering from your tests, you always have that level of excitement and discovery, right? Sometimes you also have a level of probably frustration because not all tests are probably going to be, not everything is going to behave exactly as you were expecting. But it's sort of like, I guess, a balance between the two on a daily basis that you have.
Mm-hmm. Yeah. I don't know if we have any kind of thoughts about the grander challenge in the field about fabrication. Since you're already concerned about fabrication, and now we speak about how we can have soft and hard material fabricated. For you, what do you think also other key challenges are still in the field? Yeah, we need to consider this maybe challenging, or we need really to ask ourselves hardly. We have to push more in this point.
Yeah. Well, I think, grand challenges in the field, especially from a fabrication point of view, I think there are still many. Well, don't get me wrong. I think, one of the things that is exciting the community, especially people outside of robotics that are entering the community, is the fact that there is a low barrier of entry access at the beginning, especially, I'm thinking, for example, of, soft pneumatic actuators at sort of like a centimeter scale. They've been around for almost, I guess, more than a decade, actually. And people can build them really easily. I have had students that, built them at home out of a 3D printed mold that they were able to manufacture, or even just like out of scrap materials that they had available in their homes, and they were super excited. And so that's great, I think, about our community. But from a fabrication point of view, I think there are still many challenges that we are facing when we scale down these mechanisms, and exactly, again, for minimally invasive surgical applications, for example. So I think the community right now is doing really well at building at a sort of like a larger scale. So fabrication technologies for soft robots are now being more standardized, and, if you will, becoming more reliable, repeatable, accessible, easily accessible for the large community. And I think that's very important. Like in the future, if you want to build soft robots on a consistent, reliable basis, we are approaching that very easily. In fact, we have, spin-offs, companies that are commercializing these platforms, and so that's good. But if you're looking at, again, more of a miniaturized micro scale, millimeter scale, we still have obviously challenges. Standardizing those manufacturing techniques is going to be important in the next maybe 5 to 10 years for the community. It's going to be more difficult, I would say. The smaller the scale, the more difficult things get, in my experience, obviously. Integrating, again, those sensors, those actuators, and maybe that distributed level of control that we would want in those soft micro robots is going to take obviously some more research, and that's where the challenges are going to be, but also the excitement, I think.
Mm-hmm. I think it's a good point, and I'm curious to ask you, maybe related to how to pick the problems you work on. You're really motivated about what you do because it has a potential to help people's life. But do you think, generally in the field, when we pick the problem, especially for a student, what is the criteria to choose the right problem to work on and make sure it's beneficial? So how do you see this approach? Do you think is necessary to consider what kind of problem we pick and what kind of solution we propose for the problem we choose?
So we spoke a lot until now about applicability and applied research in soft surgical robotics, for example. I think the way that you choose a problem has to deal with this aspect, but also the fundamental, questions that you want to ask. And so, having that level of curiosity towards what are the possible applications of the research that I do is good, but also, yes, you have to consider what are the bigger questions, what are the fundamental questions, scientific questions or scientific challenges that the soft robotics community and the robotics community in general is facing. And to me, that's how you choose a problem, choose an interesting problem to research on. In my opinion, again, I'm biased because I think, that surgical clinical applications are really exciting. But at the same time, to me, it is very exciting to think about what are the challenges in the robotics community. And for example, I'm thinking about how do I, approach problems of navigating into complex unstructured environments. You have that level, you have that question if you are working in clinical medical applications and if you're working in different fields, like for example, say environmental exploration or search and rescue or any other type of robot for exploration in general. So I think because robotics is an applied field, it's really easy to find a specific application in mind, but the bigger scientific questions in terms of, like, for example, how do I achieve, again, navigation? How do I achieve sensing and actuation? How do I embed sensing and actuation into the body of my robot? These sort of like bigger questions are not really part of a specific application, but they are really just scientific questions in the robotics and soft robotic community. So I think at the end of the day, you have to combine these aspects when you sort of like pick a research project to work on. You have to think about what is interesting, what is promising for the scientific community. Why would I want to solve this problem? Why would I want to work on this? Why would I want to invest my time on this? And at the same time, who cares? What's this going to be useful for?
Mm-hmm. I agree with you. Since we close the end, maybe I have a few questions for you. What could be other features do you think you would, aspire to have in the design for surgical robotics?
Well, features that are missing for soft surgical robots. I think, the field is still pretty much in its early phases, that I think there isn't necessarily one specific feature that is really well established and we have to move on, if you know what I mean. So I think, all of these aspects that we have covered so far when we were discussing the design of soft surgical robots are still, under development. There have been groups that have been working a lot on actuation, a lot on sensing, a lot of, for example, stiffening of these soft robots and combining different materials to achieve that. But there is really, this is really much of a growing and developing research field that I don't think there is a specific feature that is still completely that still requires complete research from scratch.
Mm-hmm. I have two questions for you. Maybe the first one, since you mentioned academia sometimes so challenging and not everything is working according to plan. So, for you, how do you feel that make sure you are satisfied with what you do? And if you have a doubt, how you overcome the doubt of research, for example, or the solution, and how we make sure we're satisfied with what we do already?
Oh, well, I think, there is a little bit of combining a little bit of, still being curious about what you're doing, still being self-motivated about what you're doing, I think, and resilient, obviously, about the things that you're working on.
Mm-hmm. Mm-hmm. And I don't know if you have a final question. You have received advice with a life-changing advice. Maybe it's a career or life-changing
Life-changing advice. Well, I think maybe one advice that I got in the past that was really important to me, especially as a young member of the community, maybe when I was a PhD student, was to be mindful how you spend your time and the things that you focus on and what you want to work on. Obviously, you have to. I don't want to say moderate your enthusiasm towards research, but at the beginning, I think as a young student, you tend to want to work on a lot of different things, right? And that's really great. I think having that level of enthusiasm and having that level of curiosity towards the field is really great. But at the same time, you have to publish, you have to make a name for yourself, and so you have to focus on important aspects of your work, and so you have to have that level of breadth and depth. It's really important. And then I think the other thing is it's important to have great mentors and people that will guide you throughout your career. But at the end of the day, it's also important to have a level of introspection and listen to ourselves a little bit as well, because your body, your mind will tell you what is right for you too.
Excellent. I don't know if you have any final words you'd like to say for robotics community.
Final words. Sure. Well, I think we covered a lot of sort of like more scientific and technical aspects. So maybe I want to focus my final words more sort of like on a personal, empathetic message. I think, I wish I had very comforting words, I guess, during this time, during the pandemic. But I'm thinking, especially about young researchers, young PhD students and young postdocs that are yet again going into the lab this semester. Now we are in January, so in this spring semester, during a pandemic. And so I just want to, acknowledge the fact that this is a very challenging time for them. We should be aware of the fact that, especially for people like we mentioned during our discussion, people working on hardware, hands-on types of experiments, and in soft robotics, it's definitely challenging, right? I can definitely see that level of pressure that we typically have in the scientific community to publish and to generate important, cool research increasing, because sometimes you cannot access the lab, or just there are restrictions in terms of social distancing and things like that that we have during this specific period in time. And I know it's difficult for especially young researchers, and just acknowledging that is important, and reminding these young talented people that at the end of the day things are going to improve, and you're in a field, in a community that is really vibrant and exciting to be working on. And so I think we are very lucky to be part of this, and yeah.
Thanks so much for bringing this point. I think it's very important, and it's kind of you to mention that. Thanks so much, Hala. I really appreciate your time. And such honor have you. Thank you.
Thank you. Yeah, thank you for inviting me. My pleasure.